after the video about the developer of the entropy, second law of thermodynamics for open system, here I will show two solved problems, okay, for you. Okay, I'll develop in detail. Okay, now okay, I'll give this diagram. Okay, I have mass, okay, flowing out on section 2 and 3, and flowing in the section 1. Okay, this is a pipe. Okay, and I assume that's adiabatic. Okay, so there is no heat exchange. Okay, between the system and the surrounding. Okay, but there is mass flow rate. Okay, is out here 2 and 3 sections, and 1 is in, out, in, 1. Okay, now I'll give some data. Okay, this is the mass flow rate at section 1. I don't know yet. Okay, the pressure is 4 bar. T1 is 300 Kelvin. Okay, in the section 2, I have the mass flow rate is 1 kilogram per second. Pressure at 2, section 2 is 1 bar, and the absolute temperature at 2 is 330 Kelvin. Now the section 3 is still 1 kilogram per second. Pressure at 3 is 1 bar, and the temperature T3 is 270 Kelvin. Okay. Now here I will set some hypothesis. Okay, adiabatic process. Okay, there is no heat exchange. Okay, between the system and the surrounding. Constant volume. Okay, constant volume. Steady flow. Okay, nothing is changed with time. Now the specific heat, okay, is 1 kilojoule kilogram Kelvin, and here the universal constant for ideal gas, okay, is a point. I'll raise it here. Okay. This is 0.287 kilojoules kilogram Kelvin. The same unit as Cp. Okay. Now I'll write down now the solution. Okay. Still, I will apply that general relationship between system and control volume and surface. They put here. Here's the control volume. Here's the surface control. Okay, control surface and control volume. Okay, as we did before. Now I will use the conservation of mass, and capital N. Okay, extensive property is the mass. Eta is 1. Okay, as we did before. So steady flow. This is 0. This is a continuity equation. Okay, look at here. The sign here, you see, the sign here will be positive when we leave the surface. Okay, and it will be negative when you leave the surface. Why? Because the vector dA point out of the surface, and here we can see here that dA has opposite direction, okay, of the velocity, the mass flow rate. Okay, so this is positive, okay, V, the dot product, okay, V dA, integral here in this section 2 is positive, okay, at 2 and at 3, okay, at 3. But it is negative, okay, on the section 1, because here the angle between the vector EA and the vector V, for instance, is 180. So in this case here, rho V dA, the integral, okay, is negative. So these are, we can see here, okay, look at the sign. See, 2 and 3 flow out, 1 flow in. Okay, the sum has to be 0. So M1 is the flow rate at 1. It is the flow rate at 2, but the flow rate at 3. Both, okay, measure 1 kilogram per second. So M1, the flow rate at 1 is 2 kilogram per second. So here, okay, you have this interrogation mark, okay, this is 2 kilogram per second, okay, satisfying the continuity equation or the conservation of mass. It's called continuity equation. Okay, now, conservation of energy. You see, look, the hypothesis, okay, there is no variation of kinetic energy and no variation of potential energy. So we can treat, using the energy, the conservation of energy, we can treat this as a closed system, okay? So, as you know, TdS, the derivative is a differential of enthalpy plus the volume dP. So, dI divided by T, okay, both members, okay? And I have Cp dt over T minus R dP over P, okay? If I integrate, okay, the entropy, the final entropy minus the initial entropy, Cp is a natural log of T final divided by Ti minus R, final pressure divided by initial pressure, okay? Now, here, now, balance of entropy. Attention now. The assumption, the hypothesis, the assumption is a steady flow. So this is 0, and also the adiabatic, okay? So there is no heat exchange between the walls of the pipe and the surrounding, okay? This is 0, okay? By hypothesis, by assumption. Now, this entropy generation, okay? Now you see, you have to follow the steps that I mentioned and I emphasized in the last video, okay? Now, minus m.1 S1, you see, look, let's go there, here, look, my eta is S, okay, for the entropy, okay? So I substitute, you see, my S just over here, you see, S is extensive entropy, okay? And small s is the intensive, this is extensive, intensive property. I just substitute that over here. And this is a sign, okay? The surface, there's a sign, okay? This sign, I can see down here, okay, this is 0, this is minus, because the sign of rho V dot dA is negative, inflow, okay? And it's positive at section 2 and 3, that's right here. There's a 0, okay? Follow this, okay? Follow this, what I'm saying. Okay, as I pointed out and emphasized in the last video. And here I manipulate, okay, this adequately, and I know that M3, M1 is a sum, okay, of M2 plus M3 times S1. This is M dot 1, okay, from the continuity equation, okay, that has to be satisfied, okay, and here I have this equation. So then I need to integrate. Look, I need to integrate this equation and substitute S2 minus S1 is Cp, natural log of T2 divided by T1 minus R, natural log of P2 of P1. I substitute numbers, okay? This is T2, 330, 300, and this 1/4, okay? Because P1 is 4 bar and P2 is 1. So P2 divided by 1, okay? Now, making this calculation, okay, I obtained the variation, okay, between 2 and 1. I have, let's see, I want to find out if the second law is violated or not, okay? That's why I'm calculating, okay, this entropy generation, okay? If it is positive, does not violate, okay? If it's 0, the process is a reversible process. Negative is impossible, okay? Now, I have to multiply S2 minus S1 by this flow rate over here, which is 1 kilos per second. Likewise, M.3. I will calculate S3 minus S1, okay? I have the model here. Look, I have the model. This is my model here, see? This is a model. Okay? I'm using this relationship, okay? Now, S3 minus S1 is just 1, okay? Times, let's see, S3 minus 1 is 1 log, okay? This will be the temperature at 3 divided by temperature at 1, S3 minus 1, minus, here is the universal gas, okay? This is not here, okay? The constant of gas, okay? Then I have 0.2887, natural log of 1 divided by 4. If I do this calculation here, I found out 0.292 kilojoules, kilogram Kelvin, okay? Look, S3 minus S1, okay, is the intensive, okay, not the extensive property. That's why I have kilogram over here. See? Kilojoule by Kelvin is entropy. By kilogram is the property of, it's intensive property. Now M2 is equal, M3 is equal 1. So if I substitute, look here, I will isolate. It is still isolate, okay? I'll calculate now the generation, the entropy generation here. Just substitute this number. Here I multiply by 1 and here by 1. So actually it will be S2 minus S1, okay, plus S3 minus S2, S3 minus S1. Just this calculation over here, I have 0.786 kilojoules second. This here, this is power, okay? This is power, okay? Work divided by time, okay, is power, okay? Now divide by Kelvin, and here I have a space over here, okay? If I multiply by 1000, I have watt by Kelvin, okay? This is a power, okay? This is Newton meter per second. Newton meter is joule, okay? So remember you, okay? Since the entropy generation is greater than 0, you can see here, so this implies that the second law of thermodynamics is not violated. Okay? Now, you see, there is no doubt, okay, following these procedures. They're based on the last class, okay, the last video. Okay? Now let's use the second to solve the problem here. Okay? I'll bring it here. Second question, exercise number 2. Okay? Consider steady flow displayed in the figure. Here, 1 and 2 flow in, okay, and 3 flow out. Question: is the second law of thermodynamics violated? Let's calculate the entropy generation. Okay, so this you answer my question. Okay, if it is positive, does not violate. If it is 0, the process is reversible process. Okay? If it is less than 0, it's impossible to happen. Okay, now the pressure, okay, there's the same pressure, okay, P1, P2, and P3 is 1 bar, okay. Now that's in this case, okay, is a molar flow rate. Molar flow rate. Oh, that's right here, write down the better letter. Okay. Molar flow rate. Flow rate. Number of moles by second. Okay, mole by second, the unit. Okay, this is 1, N2. N2 is 2. In this case, N3 I can calculate use the conservation of mass, the continuity equation, as we did before. Okay. Now T1 600 Kelvin, T2 450, T2 here, T3 is 400 Kelvin. Now the surroundings, the temperature of surrounding is 300 Kelvin. Don't forget, here the system here we call, do you remember, subsystem, which is this our system, okay? And this is the surrounding, okay? This is surrounding, this surrounding, okay? The temperature of surrounding is 300 Kelvin. So you see the system, okay? The heat is flowing out of the system. Obviously, the surround is receiving energy. Okay, so the surrounding here, okay, is getting energy. Okay, increasing energy through the heat exchange. Okay? Now the system is losing energy. Okay, this watt here. This is the power. Okay, joules by second. Divided by 7. So let's do the analogous calculation. But now you see this is not adiabatic, okay? Because there is exchange, not exchange. There is a heat flowing out of the system. Okay? Now it's calculation. Okay? This is conservation of mass, conservation of moles, okay, number of moles. This is mass, okay? Section 1 and 2 are negative, with the sign here, because the flow is in. Look, the flow is in, you see? Then there will be negative sign, and in 3 you'll be a positive, okay? Because the dot product, as I mentioned before, okay? Now it's quite easy. Now I divide by the molar mass, okay, capital M, both sides. Then I have the molar flow rate, okay. That's molar flow rate. M.3 minus M.2 minus dot 1. It's the same here, okay. I just divide both sides by capital M, okay. Just to remind you, okay, that the molar flow rate is the mass flow rate divided by molar mass, okay, capital M. the unit is mole per second. Okay? Now, attention now, this is not conservation of entropy. Don't use this word. It's the balance of entropy, because entropy is not conserved. Okay? Now, because you have generation. Okay? Now, assumption is steady flow. The partial derivative with respect to time, okay, of any of these variables is 0, doesn't change with time. And this is mass eta, okay, that's the intensive entropy, okay, the property, intensive property of entropy, okay. And here's rho v dot ta. Now, attention now. This heat out of the surface, you see, I know already the sign, okay? I know the sign. I'll remind you down here. Now, I will apply the same thing. My eta, okay, this is my eta is small s, okay? Don't forget, this is ds or dm, okay? A small s. And the sign is given to this dot product here. I already mentioned before. Follow these, okay? All the signs, okay? The sign plus and minus are related to this dot product over here, okay? Now, I will have this applied here, okay? This is 0, okay? But this is not 0. I have here the right-hand side, okay? That I developed before. So this is, okay? Now, just for you to understand, okay? This is mole by second, joules by mole by K, né? So just to show these terms over here, okay? So the result is joule per second, joule per second by K. So this is the power, no? This is power divided by K. So that's each term over here, each one has this dimension over here, okay? Now I will divide by m. I already divided by m, I get this relationship. Now just substitute numbers, okay? S3 minus S1, attention now, okay? The last problem, the last exercise, the previous one here, I have the P1, P2, and P3, they were not the same. So now they are the same. So log of P divided by P is 0. That term minus R that multiply this will be 0 because all the pressure are the same. And I stay only with the temperature, you see? The temperature. Quite easy, okay? Just put number, you see? S3 minus S1, S3 minus S2, okay? S3 minus S2, okay? Here, I already calculate the previous exercise, okay? And now here, without this term over here, because all the p's, they are the same. And natural log of 1 is 0, okay? Now, just Cp is given. All the temperature are here, okay? Because they don't have enough space. Look. You see the right-hand side? Now, attention now. Look. The system, I'll go there, no problem. Look. The system is losing heat, okay? As I emphasize, okay, I'll put the sign of the heat of the system right over here. See this minus sign here is because the heat is leaving, the heat is leaving the system, okay? The system is losing energy, okay? Now this is minus 8729, okay, divided by TB. TB is the boundary temperature, okay, between the surrounding and the system, which I used to call subsystem, but that's okay. Now, because I don't have much space, I continue right over here, see? And over here a little bit. These are those numbers, okay, that I calculate over there. Minus 11 dot, minus 1193, minus 687, plus this number over here. Oh, you see, this is 10.3, 10.3, which is greater than 0. So the second law is not violated. See, that's a very important result. You see, look, if you follow what I said before, you see, wait for the sign, okay, for non-diabatic, okay, at the end, you see, here in the figure, let's put over there, all right, put over here. I'll show you again the figure, which is important. Look, I have the heat flowing out of the system. Then I substitute on the right-hand side, you see, I called your attention that, and I just set minus over here. Okay? That's important, okay? Let's finish.